Hello, we are Group 11 of Dr. Greenling's AE 1601 class. I'm David Guzman.
I'm Albert Lee.
And this is our report for the glider project. For this project, we were given requirements before building the glider. The requirements were it must have wings, it must be made out of the balsa wood given to us, it must only be propelled by the force of the throw from our own hands, it must fit inside a 16 by 16 inch box, and it must not have any sharp points.
In selecting the basic components of our glider, we wanted to focus on an efficient and stable design. We chose a trailing tapered edge wing shape at a 5-degree dihedral. This was due to the fact that it offers the most lift at the cost of maneuverability, which is unneeded in a simple glider. We also chose a V-tail at a 45-degree dihedral over a conventional shaped tail because it has less drag, is more stable, and has less parts to construct. For our fuselage, we rounded and dramatically tapered the stick given to us to allow for proper balance along the length of the fuselage. To construct our glider, we first laser cut the wings and tail, then we sanded down the fuselage with the belt grinder and sandpaper, and then lastly we constructed the glider using superglue.
After constructing our glider, the center of gravity was initially right behind the wings. This caused for our very first test throw to pitch a lot and ultimately flip in the air. After all changes were made to the final design, the center of gravity was about 3 inches from the nose. In order to find the coefficient of lift, we estimated our angle of attack to be about 5 degrees. Then, using the coefficient of lift versus angle of attack graph for a flat plate provided to us in our aerodynamics lecture slides, we estimated the coefficient of lift to be about 0.55. Then we checked with the formula coefficient of lift is equal to 2 pi times the angle of attack to confirm our results. In order to determine the coefficient of drag, we used the coefficient of drag versus angle of attack graph for a flat plate, also provided to us in the aerodynamics lecture slides. With our estimated angle of attack being 5 degrees, we estimated the coefficient of drag to be about 0.05.
In the end, the glider performed adequately, flying 41, 50, and 30 feet respectively in our final flight tests. We had several ideas in mind that we believed would have boosted our performance, although we were unable to implement some of these planned changes due to a manufacturing error that ruined the material. One planned modification to the design was a better center of gravity. Although we did trim the original glider with weight to allow it to fly properly, we wanted to shape the fuselage more accurately to ensure better weight distribution without the use of more inconsistent materials such as Play-Doh that we used. Additionally, we wanted to fix the glider's tendency to roll during its flight by more accurately manufacturing and assembling the wings and tail. Lastly, we considered adding a tapered wing shape to the tail, as it would have been a little more efficient than the rectangular wing shape of the original tail.
Overall, the project was a fun and interactive way to apply the basic aerodynamic topics that we learned in class. It was interesting to use formalized concepts as the basis of our design, and also rewarding to confirm these concepts through our multiple flights.
If doing this project again, we would place a greater emphasis on correct balance from the beginning and then design around that, as it was the singularly most important requirement for a successful flight. Additionally, a more robust design with longer wings would have allowed for the airplane to fly more efficiently and stabilize after a more forceful throw, as proven by the results of the flight test.
And finally, these are our citations.